4, 3, 2, 1. Yay! We're live. All right. Welcome everybody to a mixed hybrid. This is the first time that we have both the virtual session, which we did over the last 2 years, a couple of times, and we have a live audience, which you probably can't see, but here are a lot of people eating gyros, smelling like garlic, which actually is great to see that after 2 years, finally having people in the office and having a live meetup. So I'm pretty excited, pretty nervous to have that also for the first time. I think we have a great program for you guys. Two amazing talks. I have to admit that I cheated a little bit with the title. I don't know whether you recognize it, Fabian. The title was Content Recommendations at Yodel.com and Spiking Neural Networks. This is a shorter title because I didn't feel it didn't fit into the meetup.com title field. So the actual real talks you're going to see is content recommendations for hyperlocal communities. Is that correct?
That is probably correct.
All right. Hyperlocal communities, our talk number 2 is a guest speaker from Yodel.com at Germany. The only hyperlocal community I know is next door, and I constantly am being bugged about cats. I think I should have found 2 cats every day somewhere in my garden. I think Yodel.com has a pretty unique concept and idea, which Fabio will explain to you, and also pretty exciting challenges with content recommendations for hyperlocal communities. So I'm really happy that Fabian could join us here from Cologne. The first talk, which we're going to start with, is not spiking neural networks, or it's also about spiking neural networks, but it's about how to energy efficiently use neural networks and actually do it like our brain does it. Goes pretty deep, so I hope you have to use your brain as well. That is a speaker from Dataworkz, and this is actually a talk that he will be presenting in San Francisco at the ODSC. So this is a premiere tonight, pretty excited to see what Olaf has to say. I think that's basically it. You'll be watching via YouTube, which means it's for the audience online. It will be a little bit more difficult to interact. Please, if you have any questions, ask them in the chat. I will follow it and will present them to the presenters, and they will be answered. If you have any questions afterwards, just let me know, and we'll be answering them either live or later on via email or chat communication. And the audience here, I think the best thing is just to ask questions, but I leave that actually up to the presenters, so how you want to do it. I think I'm finished, right? All right, time enough. Olaf, kick it off.
Okay. Okay, thank you. For the people who can see me, I'm on vacation. This is not my own furniture. You see behind me. There's a beautiful lamp, but this is not mine. Tonight I'm going to speak about spiking neural networks. This is a kind of neural networks that has been invented a few years ago, but I think very few of us have heard from it in the last years. It's always about deep learning, convolutional neural networks, and other state-of-the-art stuff. But yeah, well, you never hear about spiking neural networks, but they are quite interesting, and some researchers call it the 3rd generation of neural networks, which is the follow-up on the deep learning neural networks that are currently widely used. I think I can skip this slide because Martin already introduced me. I'm a data scientist at Dataworkz. I got inspired by spiking neural networks when I was reading a magazine I have a subscription on. There was a short article about it. And when I read it, I started Googling to spiking neural networks. I was looking for it on the internet, and I found pretty much news articles, all with headers like spiking neural network promises improved AI, and all the titles, all the headlines of those articles were saying the same. Is this a breakthrough for green AI or a breakthrough in energy efficient artificial intelligence? And that took my interest, and I started to look into this. What are those kind of networks, and why haven't I heard of them before? And why all data scientists I know always work with deep learning, convolutional neural networks, and never use spiking neural networks. But there must be something wrong with them. Why is never anyone using it? And that's also a little bit the thing I want to share with you tonight. The presentation is pretty conceptual. I will explain what spiking neural networks are, and what are the challenges, why are they not widely used yet. And I want to show some frameworks that already have been developed so far. And I will pretty much, actually I will want to share with you what those kind of networks are. It's not too technical, as Martin promised. There are some mathematical details, and a little bit of code, but I try to keep it simple for the people with lesser knowledge of mathematics. And at the last slide, I have some references to some articles where you can read further if you are interested. I start with the success of artificial neural networks and the downside. Why have people invented spiking neural networks? I will explain where the inspiration comes from. It comes from the human brain, and I will try to explain how that works. Then the transition from the brain to an algorithm. How do we translate the way the brain works into an algorithm we can code? A short demo. After the demo, some challenges for the spiking neural networks, some ideas to overcome those challenges, some solutions. Again, a short demo with one of those ideas demonstrated. And finally, some research results from researchers that are working with spiking neural networks to improve them, to make them ready for usage among data scientists. So, artificial neural networks. The subtitle is the downside of their power. So it's actually twofold. It explains that artificial neural networks are very powerful. We all know several examples. For instance, this is the architecture of AlexNet. It consists of 8 layers and 60 million parameters. So it's very complex. Another example is BERT, the NLP model. And these networks are very complex. They have very much calculations, and that comes from their continuous nature. Each input on the left side goes through every layer, and it has to execute many calculations to come to the final layer. They perform very high, but due to the many calculations, it costs a lot of energy to train them and to use them, and that's actually the downside. So on the one hand, their performance is very, very good, but it takes you a lot of energy, a lot of calculations to come there. So one of the downsides is large energy cost, and that's a downside for instance, for always-on devices. And a second downside may be that it's a bottleneck for efficiency in applications with real-time interaction. For the purpose people using these models, it's perfectly fine. They work very good, very in many applications, but it can be more efficient, and that's exactly where spiking neural networks come in. And the inspiration of spiking neural networks come from the human brain, and the human brain consists of very much neurons. And I'm not a neuroscientist or a neurobiologist or something else, so my explanation may not be very accurate, but I will try to explain what I read about it. And well, the brain is full of neurons, and each neuron communicates through voltage spikes. A stimulus comes in. That means a receptive field of a neuron detects a signal. For instance, when you look outside and you see a red traffic light, one of the neurons recognizes the red light, and a stimulus comes in at the left bottom side, and a spike, a nerve impulse, travels through the axon, following the arrows, until the axon terminal on the right side. When that signal arrives at the axon terminal, it releases neurotransmitters. Those are the purple triangles in the middle. And those neurotransmitters travel from the presynaptic cell to the postsynaptic cell. One neuron transfers the information to the next neuron. And those neurotransmitters attach to the receptors at the postsynaptic neuron. And there are two kinds of transmitters: excitatory transmitters and inhibitory transmitters. And the first one causes an increase in a voltage potential, and the second one causes a decrease in voltage potential. And when we look at the excitatory neurons, which cause an increase in the voltage potential, when enough neurotransmitters travel to the postsynaptic cell, then the voltage potential will continuously be increasing. And at some point, a certain threshold is reached. And when that threshold is reached, the postsynaptic neuron will itself fire a new spike to the next neuron. If that threshold is not reached, then nothing happened. The voltage potential in the postsynaptic cell will slowly decay to its resting potential until a new spike comes in. That's very high level from what I understood the human brain works. And well, now is the question, how do we come from this phenomenon to an algorithm? Well, the first thing we have to think about how do we translate this to mathematics, the interpretation of the neuron in the brain. Well, that means that the input, the things we put into our model, for instance, images or the handwritten digits in the MNIST dataset, we have to translate them into spike trains. We cannot put an image into your model. Now we have to translate them into spikes, because we saw in the previous slide that the human brain works with spike signals that travel from one neuron to another. Those spikes lead to a change in the potential difference. So we also need a model that can deal with the spikes and that can measure that potential difference and do something with it. And we have to keep track of the voltage potential, and when that voltage potential, when a threshold is crossed, then the neuron has to fire a spike by itself. And this may make things more clear. Here we see at the left side, we see in the red lines, those are input spikes. So you have to translate it, an input image into a spike train, and this is the resulting spike train, all those red lines. Every time every time that a spike comes in, so at every time step on the x-axis, the blue voltage potential goes up. So every time you see a red line, the blue line goes up. Immediately after the blue line went up, it also starts decaying back to its resting potential, which is 0. So you see after in the middle of in the second spike train, then you see that the blue line crosses the yellow dotted line, which is our threshold, and at that point, an output spike is fired. That's the green cross. And in the first 3 spikes, it didn't lead to a threshold pass, so no output spike was fired there. Schematically, you can look at the image B, and at the top, the spike comes in. Here we have some logic, and that updates the voltage potential. That's the blue dotted line. And when that voltage potential crosses the threshold, then it goes out with an output spike at the bottom, at the arrow to the bottom. And the abbreviation LIF stands for leaky, integrate, and fire. And that brings us to the next slide. So we saw that that term, leaky, integrate, and fire. Well, that's a simplification of the Hodgkin and Huxley model. And Hodgkin and Huxley, they won a Nobel Prize for their model that describes how action potentials in neurons are initiated and propagated. But this model is slightly too complex to build spiking neural networks. It's not necessary. Then that takes also a lot of computations. So the leaky integrated fire is a very useful simplification. It looks a little bit like this. So the input current represents the spike. So a spike comes in, it's a current, and you have a resistor and a capacitor. And when a spike comes in, the voltage potential goes up. And when that voltage potential crosses a threshold, like I already explained, then the spike is fired, and that's the arrow that goes to the right. And this voltage potential that can be described by a differential equation, and this is the first mathematical thing I will tell you about. You don't have to remember this, but it's just to give you an idea how it works. So this results in a differential equation, and when you draw a graph, they would look something like this. So on the y-axis, we have the voltage potential, and on the x-axis, the time in milliseconds. At time step t1, a spike comes in, and the voltage goes up. When the voltage is at its maximum, it starts to decay to its resting potential. That's the red line. If no spike comes in, then it goes back to U rest, following the red line. But at time step t2, a new spike comes in. So the voltage wasn't already back at its resting potential, but it goes up, caused by the new spike at time step 2. Another one comes in at time step t3, I would say, and so on. And at a certain point, it crosses a threshold. And at that threshold, a new spike is fired. And this is basically the whole concept of the leaky, integrate, and fire model, which is described by a differential equation. So now I have explained how the model should work. That's basically the leaky, integrate, and fire model we can use. But when we start, then we have to start with how do we create a spike train? If you, for instance, want to use the MNIST model, we will look at it later in an example, then then you have to translate those images, the handwritten digits, into spike trains. So how do you do that? A good a way to do that is to convert an image with a Poisson distribution. And a Poisson distribution is a probability distribution, which is widely used in mathematics. And what it actually does is you take an interval of, for instance, 250 milliseconds. You divide that interval into small pieces of length delta, and you have a pixel intensity rate of lambda. The pixel intensity rate here represents for instance, the grayscale of the handwritten digit pixel. And the number of spikes in an interval delta with an intensity rate lambda is then Poisson lambda delta distributed. This means that I have here a picture that explains how you divide the interval, but that's, I think, the easy part. But a Poisson lambda distribution means that you can, with that information, you can use math to calculate the probability that n spikes will occur in an interval delta. And it also means that the higher the intensity rate, the higher the probability of events or spikes in our case will happen. So that means that if you have an image, a handwritten digit image, and the pixel is just black, a very low intensity rate, then the probability that a spike will occur is very low. When the pixel is white, which is a very high intensity rate, the probability that a spike will occur is very high. And that, in that way, you can translate those images into spikes. And then you can just measure on the time axis at each time interval when a spike will occur. And here you see the first spike at T1, second spike at T2, and a third spike at T3. With a higher intensity rate, more spikes will occur. With a very low intensity rate, we see no spikes at all. So I will show this. I will show you this with a short demo. Then I have to share my other screen. Let's see, where is it? The example I want to share with you is based on one of the frameworks that has already been developed for spiking neural networks. That's the framework I'm talking about is called BindsNet. I will mention it later again. And what we're gonna do is we will see in this example how this Poisson encoder will work. How do we encode images from handwritten digits into a spike train? Now, first of all, I load some libraries. The BindsNet framework has a Poisson encoder, so you don't have to understand the math I just talked about. It's already top of the shelf. You can just use it. You can also import the MNIST dataset, and it's what also is useful is to say is that the BindsNet framework is based on PyTorch. Many data scientists already know PyTorch. So if you know PyTorch, then, well, this is not really hard to understand. Then we set some parameters. We define an interval time, for example, 250 milliseconds. I take the interval length of 1 millisecond. So I have 250 intervals and a pixel intensity rate of 128. And this is the maximum firing rate in Hertz. Then we load the MNIST dataset. And this is the MNIST module from the BindsNet datasets library. And you say image encoder is the Poisson encoder, and with an interval time of 250 milliseconds and an interval length of 1. This function will download the dataset. I've already downloaded, so goes pretty quick.
Hey,
And your
Olaf,
dataset is now the following
Olaf,
keys. It has
can you make the
there's a set
screen
of
a little
images,
bit
a set of labels.
louder?
Bigger? I don't know. What's the? Is this big enough? Is this big enough, like this? I'm not sure. I don't know how to zoom in this. No, that doesn't work. Oh, well. Okay. So our dataset has a set of images, labels, and encoded images, and also encoded labels, but we will not look at that. And let's look at an example. Well, the first element is a 5, a handwritten 5. If we look at the pixel in gray levels, then we know that the pixel, the image has a shape of 28 by 28 pixels. And we see here in the middle rows, the pixel intensity rate is higher, and on the top rows, it's all 0. And we can see that in the image as well, because the top rows are completely black. Now we're going to translate this into a spike train. So we read out the encoded image set from the dictionary, and this encoded image has a shape of 250, which is the timing interval into intervals, into 250 intervals, and also the image is still 28 by 28. If we now look at how these spikes are divided among the rows, and you see that the first 5 rows has no input spikes at all. Those rows were also almost completely black. I think this is the fourth row. So those are completely black, and there were no spikes at all. And here spikes are coming in. So this is also what you expect. There are more white pixels, gray and white pixels, so you expect more spikes, and this is exactly what happens with this Poisson encoder. And we can plot it into a bar chart, and with a little bit of fantasy, you can recognize here a 5 in it. And you see the most spikes are here in rows 6 and 7, and well, at the bottom, a lot of spikes as well. And this is indeed how the 5 looks at this image. Here are the most white pixels, and at the top 4 rows there are no white pixels, so there are no spikes at all. And this is the way you translate an image into a spike train. All right, let's go back to the presentation. There. The final step we have to think about is how to measure the spikes. So now we have a method to encode spikes from an image, translate them into a spike train. We have a method to model for a model, the leaky integrated fire model. But how are we going to decode the spikes? There are several ways you can do that. You can use rate coding. You can see that in picture A. This is simply counting spikes in a time interval. That has some disadvantages. Some neurons may fire the same number of spikes. So what are you going to use? If you remember, there's a sort of reset mechanism. After a spike was fired, the voltage potential decays to its resting potential. If you have a too tight reset mechanism, that may reduce the firing rate of a strong neuron. And a real-time readout is also not feasible. You have to wait until the interval has finished. Another thing you can use is binary coding. This is very simple. Just has a spike we've fired or not, yes or no. The downside of that is it ignores the timing nature of spikes. So you are only going to say, yes, a spike was fired, but you're not going to say, yes, a spike was fired, but it was fired very, very quickly, which may represent a strong neuron. You can use latency coding that you can see in picture C. There you use the length of the intervals between spikes, and closely related is the rank order coding. Then you simply say, all right, neuron 3 has the first spike, neuron 1 has the second spike, etc. And the last option, well, not the last, but the last example I will give here is first time to spike. And that is the method, the other framework I would show you, SpikeTorch is using. And it's just it is just a measurement of the first time a spike was fired, and it's that's the advantage is that it is very fast, and you need only one spike to work with. So now we come to the challenge, and that will give an answer why spiking neural networks are not widely used yet, and most of the data scientists, machine learning engineers still use the well-known deep learning networks. You see a picture of a fully connected convolutional neural network, and what's happening in this network is an image goes in, it goes to every layer, and in each layer you have matrix multiplication, you add some bias, and finally you use, for instance, a softmax function or a ReLU function to come to an output. And the advantage of that is that the functions are all continuous, and except for the value function, but that one is almost continuous. And that's exactly what we need to train a neural network, because training a neural network uses gradient descent, like you might know. And gradient descent is based on taking the derivative of a function. And you can only take the derivative of a function when that function is continuous. So in these deep neural networks with matrix multiplication and some softmax function or sigmoid function, which are all continuous functions, we can use backpropagation with gradient descent to train those networks. If you look at a graph of spikes that happen, this is clearly a discontinuous function. And along the time axis, the derivative of this function is almost everywhere 0. And each time a spike is fired, the derivative doesn't exist, because this function is discontinuous. So we cannot use gradient descent to train a network. And that's simply the biggest challenge in the usage of spiking neural networks, that it's very hard to train them. So how are we going to solve this problem? There are quite some ideas and solutions which have been suggested over the years, mainly by researchers at universities, which are who are doing research to these networks. And I will give a few examples. One of the examples is, for instance, a sort of transfer learning. it's between quotes because it's not exactly transfer learning, but the idea is that you train an artificial neural network, then you transfer it to a spiking neural network. So the training is done as a regular artificial neural network, and then you use it in a spiking neural network way. You can use a linearization of the spike generation process, or spreading out the spikes, which are all tricks to make the spike trains more continuous, so that you can use gradient descent. There are also some popular unsupervised methods, and I will give an example of this shortly after the slide. And that is spike time dependent plasticity. This is a form of Hebbian learning, and that says that that's a process that strengthens a synaptic weight. If the postsynaptic neuron fires shortly after a presynaptic neuron has fired, then the weight will be strengthened, and it will be weakened otherwise. So if the time between the postsynaptic neuron fires and the presynaptic neuron fires is greater, then the weight will be weakened. And the slogan of Hebbian learning is also fire together, wire together. So if two neurons fire closely after each other, then the synaptic change will be big, and otherwise will be small. You can see that in this graph. When two spikes were fired shortly after each other, the synaptic change is big for positive values, or very low for the negative values. And that's the concept of spike time dependent plasticity. So these are some ideas to overcome the challenge of the discontinuity of the spike trains, and some frameworks that have been developed use these methods. One of the frameworks is BindsNet. We saw this one in the demo. And they say this is a Python package used for simulating spiking neural networks. And SpikeTorch is a PyTorch-based simulator of convolutional spiking neural networks with at most one spike per stimulus. That's the thing I already said. SpikeTorch is especially developed for convolutional neural networks, and they work with the first time to spike method. BindsNet, by the way, is developed by researchers at the University of Massachusetts, and SpikeTorch by researchers at the University of Tehran in Iran. What they say about the methods by themselves is that BindsNet is more flexible and general, and SpikeTorch, like I said, is especially focused on convolutional neural networks. And it's very, very interesting to look at their GitHub pages, because there are very easy tutorials, examples you can look at. And I will now show you again a demo, but I think I will only show the picture I have in the demo, because since the font is very small, that's easier to give an idea how that spike time dependent plasticity works. So the first cells we already saw in the previous demo, and this is the network BindsNet uses in their in an unsupervised way to learn to train on the MNIST data set. And this works with spike time dependent plasticity. So the idea is as follows. Here you have an input picture, which is in this case the 0. This picture is translated into a spike train. And the pixels are connected to all of the neurons of this excitatory layer. And the number of neurons on the excitatory layer you can choose by yourself. For instance, here there are 100 neurons. So all the pixels goes to every neuron in this layer. The weights of this layer are randomly initialized. And here we use the spike time dependent plasticity and the leaky integrator fire model I earlier explained. And the excitatory layer is connected one-to-one with the inhibitory layer. So when a zero comes in and it goes here to a neuron with a certain weight, you just measure how shortly after the spike fires, the excitatory layer also fires a spike to the inhibitory layer. If this is very fast, then the inhibitory layer is on his turn connected to all of the excitatory layer neurons except for the one it receives its connection from. So this neuron on the top left on the inhibitory layer is connected to all the neurons in the excitatory layer, but not on the top left neuron. And what it does is, if this neuron fires very short after a spike comes in, which means, okay, this is the spike time dependent plasticity rule, fire together, wire together, then this inhibitory neuron will inhibit all the other neurons in the excitatory layer. And when you do that, those neurons will learn on which digits they have to fire. And once you finish training, then you will add you will add the labels to those neurons. So this is an unsupervised way, and you might end up with something like this: 100 neurons. With some of them learn to fire at a 7, some of them fire at an 8, etc., etc. And this is an unsupervised way BindsNet have developed to train the MNIST dataset. BindsNet has also developed a supervised way, and it works pretty much the same. They have only have an extra parameter, and they call it the clamp. And I don't know very good the details of how this works, but it works pretty much the same, but in a supervised way. All right, back to the presentation for the final slides. So those were some solutions. They have been by some frameworks, and those solutions are already a couple of years old. And spiking neural networks are still not very popular in the field. And recently, other solutions have been proposed by researchers. They, for instance, the CWI, the Centrum voor Wiskunde en Informatica in the Netherlands, is doing much research to spiking neural networks. And they use a solution which is called surrogate gradients. That means, well, the word already explains itself. If a gradient doesn't exist, then you use something that does exist instead of of this gradient. My first bullet on the slide says spiking neural networks perform worse than artificial neural networks when it comes to accuracy. That this is still the case. But those new solutions of surrogate gradients, they have been proposed to gain better accuracy, and those spiking neural networks with these surrogate gradients come pretty close when it comes to accuracy, and we will see that in the last slide. And what are surrogate gradients now exactly? So you substitute the non-existing gradient with a derivative that does exist. Here the last bit of mathematics. For instance, you are you can use a stochastic gradient. Here you see a Gaussian distribution, or you can use a sigmoid function or a ReLU function instead of the non-existent gradient for the discontinuous function. And here in the picture, the purple line is has zero derivative everywhere except for when a spike is fired, then the derivative is not defined. So instead of using that function, you can substitute it by a function that has a derivative. For instance, the green function, which is a piecewise ReLU function, or you use the yellow exponential function instead. And those are the latest developments from last year to improve the accuracy of spiking neural networks and to make training more easy. Well, what are some results currently? This comes from an article by a researcher from the Centrum for Wiskunde en Informatica I just mentioned. Here you see the best for the MNIST dataset. The best result is a dense indirect, I think, recurrent neural network, which has an accuracy of 99.48%. But the ReLU spiking recurrent neural network has an accuracy of almost 99%. So this comes pretty close to the dense recurrent neural network. And it's already better than the LSTM neural network, for instance. And this researcher did the same comparisons on several data sets with several types of neural networks. And the most interesting, where it all started, that it's more energy efficient, we can see in the last table. And it's for instance in on the SHD 256 task. I have to admit I don't know which dataset this is, but he made a comparison between a bidirectional LSTM model and an adaptive spiking recurrent neural network. The accuracy of the spiking neural network is a little bit behind of the LSTM neural network, but when it comes to the energy ratio, this is set to 1, and the LSTM neural network is almost more than 1900 times less efficient than the spiking recurrent neural network. And well, you can check for the other ones as well. The regular LSTM is 965 times less efficient. So there's so here the spiking neural networks wins against the LSTM neural network. So when it comes to accuracy, the artificial neural networks are still a little bit better, but spiking neural networks are getting better and better, and a lot of research is done currently, especially I think only at universities. Data scientists who works at companies on projects will always use deep neural networks until very useful frameworks have been developed for spiking neural networks. But I think there's a great future for these type of neural networks. So I will follow the developments on this, and let's see where it goes. And that was the last slide. If you have any questions afterwards, tomorrow or anything, you can send them to me. At my GitHub page, I have the code examples I showed you in the presentation, so you can download it if you want. But those examples are based on the BindsNet framework. So if you really want a very good example, you can better check out the GitHub page of the BindsNet page. So that's it. And yeah, on the final slide, there are some references of interesting articles I read for this presentation. So if you are interested, you can check these out and read them yourself. These articles are much more mathematical than I try to keep it more conceptual, but here they in this articles they are going deeper into the math. So that's it. Thank you. And if there are any questions, let me know.
All right. Thanks a lot, Olaf. You got some real applause. We have some questions here already. I see 1, 2, 3. Let's start with you, Daniel. David.
Thank you. Yeah, I'm trying to get my head around exactly what the input of the network is. So you have, as far as I understood it, I'm trying to recap it. You have an image, and then you say every so many seconds you see if neurons that are connected to the image will spike. So it's basically you just put the image, for example, 100 times in a row and see how often the neurons will spike, and if they spike less, the decay goes down. So then is it okay? Wait, let me rephrase it. Is the initial input something like the image 100 times or 10 times or?
No, the image is presented just once, and it's presented for a time frame. So it's more time-based. So you present the image for 250 milliseconds, and then you measure the spikes that occur on every pixel in the image.
But there was an interval. So if it's 250 milliseconds and it's a 1 millisecond interval, then it's basically 250 inputs. That's how I get it. But I'm not sure if I understand it.
Like that. Yeah. Yes, then you're correct. So the input, I understood your question wrong. Yes, you divide the time interval of 250 milliseconds into short intervals of 1 millisecond or 10 milliseconds. And in that, you can say then the image is presented 10 times or 250 times, exactly. Yeah. And you, based on the decoding mechanism, rate coding, binary coding, you measure the spikes, and then you look at for instance, at the excitatory layer, how often the neurons will fire after the input spike.
And the spikes are 0 or 1, or are they graded?
That depends on the decoding mechanism. In the example I showed you, there they are 0 or 1. They use binary coding, but you can also use rate coding, and then it might happen that 5 spikes were fired into an interval, and then the input is 5 and not 1 or 0.
Thank you.
All right, we had more questions. I think Leonard and then Guido.
Yeah. On the choosing the derivative in the case of the discrete distribution, how do you choose the right derivative there, the right approximation? Because I can imagine it's really hard to get a derivative approximation of something that is 0 for most of the time. Is that a matter of just like doing a grid search and hoping you get the right answer, thereby adding a lot of computational overhead, or is there like a more structured approach?
I think this is more a matter of waiting for researchers with more knowledge than I have to get an answer on that. The ideas of surrogate gradients, the articles I read are from last year. It's pretty new.
Okay, thanks.
All right, Guido.
Yeah, so you talked about this Hebbian approach to learning, where things fire together, wire together, right? Can I see this as the network doing a dimensionality reduction? So replace a whole bunch of waveforms with a single waveform. Or, yeah, sorry, it's Did you hear the question?
No, I'm sorry.
If you come over here, then yeah. So yeah. So you talked about this Hebbian approach to learning, where whenever stuff fires together, they wire together, right? So can I see this as this wiring together as an approach to reducing the dimensionality, so that you can, for instance, take a whole bunch of complicated signals and send them down single communication line in a compressed format?
No, you have to see it as an update of the weights. In a regular neural network, you use backpropagation to update your weights. Some weights increase, some weights decrease to train your network. And this spike time dependent plasticity will just update the weights and make some weights more important. For instance, when it sees a 5, and other weights less important. So it's not a dimensionality reduction principle, but more it's just a method to update the weights, because it's in fact an unsupervised way of learning.
Okay.
I see you thinking. Some more to think over, or
Yeah,
all right.
Otherwise,
We'll have a huge
yeah.
discussion, which is always interesting. But we have another topic which I'm pretty excited to have here, because he's coming from Cologne. Fabian, maybe you could get your laptop started. Cologne is where I originally come from, has one of the best beers. So we'll see what Fabian thinks about our Dutch beer.
I'll try that later for sure.
He'll try that later for sure, absolutely. I am, Yodel.com sounds more Bavarian to me, so I'm very curious where that name comes from. But of course, hyperlocal communities, and how do you recommend for that? That will be your topic. So kick it off, Fabian.
I will.
And the audience is yours. Please feel free to ask questions. Right,
yeah, sure. Also, feel free to interrupt me. I think that's way easier now in a physical meetup. So just raise your hand or something like that. And then I'm also happy to take on questions immediately. In fact, actually, on the first question, I might even have to pass. I don't actually exactly know where the name comes from, but it definitely is more towards Bavarian than Yodeler. But to be honest, I don't know where the name originates from. Okay, now. Okay. Okay, cool. That works great. Right. Are we good to go? Okay, perfect. Then, yeah. Good evening, everybody. First of all, Martin, thank you very much for the invitation. And yeah, I'm really happy to be here actually in person. It's actually also for me first meetup after probably being at home or in the office for 2 years. So I'm really excited. I'm really looking forward to talk to you guys here tonight. So yeah, my name is Fabian. I'm here from Yodel. I'm going to talk about content recommendations at Yodel, and maybe quickly as a short agenda for tonight. First of all, I will talk a little bit about Yodel, what Yodel does exactly, maybe also give a little bit context about the hyperlocal character of Yodel. Then I will talk about a very simple way of recommending content, which is not even personalized, just called hot sorting. And then I will give a short introduction to collaborative filtering. So my talk today is definitely not state of the art, I would say. It's rather something well known, but it's a very simple way to get started with content recommendations. And it's essentially, at the end of, you will see 10 lines of Python code, and you could reproduce that, given you have the data, of course. And then lastly, there will be definitely time for a Q&A. Yeah, so what is this talk not about? So this talk is not about the latest state of the art, as I already said, because we are a startup. And if we compare certain aspects, and for example, availability of code that is actually functioning is more important to us than 5% more F1 score. Also, if you think about the talk that we just saw, deep learning and those kind of things, we're also not using deep learning for recommendations right now, because on the one hand, you will see in the literature There's also a lot of work recently which actually doubts the usefulness of neural networks for recommender systems. They do definitely have their place, but maybe not when it comes to recommendations. And it's also a question of cost. I mean, we all know GPUs used for deep learning, and if you're now in a hyperlocal setting, and if you want to do recommendations for dozens, hundreds of communities, then it can also be quite definitely a cost factor. And last but not least, this is also not about content-based recommendations. And I will also give a few more details why we are not doing content-based recommendations, but maybe let's quickly start. Goal, I mean, I would be happy if by the end of the evening, you guys actually take it as an introduction and feel like, okay, I want to give it quickly a test if I have a certain data set and just run the code with a few lines of Python and essentially have an idea what you can achieve with it. And also, I also want to talk a little bit about potential trade-offs that you will face when you actually develop a recommender system. And lastly, also, I want to make you aware of the potential pitfalls that you might encounter when building a large-scale recommender system, in particular in this hyperlocal setup. So what is Yodel? Actually, first slide about me, so maybe a small fraction of Yodel. So yeah, I did a PhD in probabilistic graphical models, did it at the University of Dortmund. Afterwards, I co-founded a startup that was offering a predictive analytics service where we would do churn prediction, purchase predictions, and those kind of things. And now since last year, May, I'm head of data science at Yodel. And if you guys have any questions after the talk, feel free to ping me on Twitter, LinkedIn, or whatsoever. Also happy to answer questions there. But now the more interesting part, what is actually Yodel? So Yodel is a hyperlocal community. And we are an app that works on iOS, Android, and when you use Yodel, you see content from other Yodel users in your area. So it is somewhat maybe similar to Nextdoor, but we also differ in certain aspects. For example, there are no profiles on Yodel, so it is somewhat anonymous. And it is also that we are only working on apps, essentially. There's no web version or something like that. And when you share content on Yodel, other people can vote, comment on your content, and by voting and commenting on content, you can essentially influence what your neighborhood talks about. And I think there are various great use cases, and as we finally now can all leave our homes again, we have also again more to share. So for example, people also meet each other for events. For example, if people go for a run or something like that, people want to know where there's a good restaurant in the area, and so on and so forth. So there are plenty of use cases, and I think it's really the main distinction for us is also that we are hyper-local. So people really talk about local content. And there's, yeah, sure.
Where you actually are at the moment right now, or do you specify an area that where you're interested in, like Nextdoor, for example?
It is actually the area where you are right now, but we also have things like hometown feature. So for example, when you're traveling, but you want to be in touch with your home community, you can use our hometown feature. And we have also something called the Explorer feature, which I think was also a feature which was partially done now during Corona to allow people to move in other areas. But the primary use case is really knowing what's around in your area. And as we are active in various different countries. We have millions of users, and with that, you can also imagine that we are tracking hundreds of millions of events every day. And this, in general, is a very interesting data set, combined with the content in forms of images, videos, polls, text. It's a huge amount of data that we track every day, and also just the interactive data already gives a very interesting data set to work with if you are interested in data science and data. So, wrong direction, that one. So what are the applications of machine learning and recommender systems at Yodel? I mean, there are various use cases, and I think probably could be 5, 10, or 100 times as big, and we would still have more use cases. But there are obvious things like bot detection, for example. If you're a platform like ours, there are always, let's say, malicious players who come with their own intent, which is maybe not in favor of what we plan to do. So we want to detect them, obviously, automatically, as one example. Then there's also image moderation, which is a very interesting use case and where we actually do use deep learning. So if you are an app on the App Store, you are not allowed to have, for example, not safe for work content, for example, nude images in your app, and you need to remove them. But if you have millions of users, you also have a small fraction of users who love to upload nude pictures, and we don't have the resources to check all of them by humans. So here image moderation is a very nice use case where we trained deep learning models to classify images, and we could significantly and substantially reduce the amount of images that actually need human moderation. Besides that, then there's also text classification, but this is definitely, let's say, still at a simpler stage at Yodel right now, but it's simply essentially identifying intent of a content and something like that, or classifying posts into, let's say, jokes or pieces of information, requests for helps or something like that. And then is of course the topic of tonight, which is recommender systems. And then there are also various areas. So similar to other social networks, we have a feed which you could personalize, but of course you could also personalize push notifications, because of course I would rather like to see a push notification that is close to my interest than random ones. And then we also have a concept of channels, for example. I mean, if you may be familiar with Reddit and Reddit subchannels or subreddits, we also have channels where people collect certain topics of interest. And then, of course, what would be a good channel for a new user to follow, for example. And tonight I am actually focusing on the personalization of the main feed, because this is one of the big topics that the data science team currently works on. So what does that actually mean? So here are two screenshots essentially of two versions of the app that we're currently testing. And if you open, for example, now here, Yodel, you would see a main feed that is just chronologically reverse ordered. And now with the algorithmic read, we are trying to add a fourth option here. What you can see here is this icon. And we give you content that is not only the newest content, but we also show you content that you have missed. And of course, our mission is now to find the best content that you are interested in, but missed because you weren't online for 6, 12, 24 hours or something like that. And right now we have essentially 3 standard sortings in the main feed. You can see the newest content, you can see the content that is most commented or loudest. And right now we're playing around with different setups. And also I think what's important to mention here, it is not only a technical challenge, but it's also a product challenge, because I can tell you, adding a fourth feed, then many people will just return to the newest feed because they're maybe used to that and they don't want to see recommendations or something like that. Or if you go more drastic steps and remove all of the sortings, users are also not always happy because they're missing certain aspects. But still, these are essentially the main challenges that we're working on. And at the end of the day, we want to provide a better user experience than just showing the newest content on the platform. And the first approach that we took, or that we are also still working on, is something called hot sorting. So what is hot sorting about? It is a non-personalized way to make recommendations. And it's a very simple idea that you just rank your content by the engagement a post receives. So for example, you could just sort it by votes. But of course, you don't want to always recommend years old content. You also want to combine it with recency. So there's very simple formulas that you just take a lot of engagement, divide it by the age of a post, and then you get a ranking essentially. So you could have, and then depending on how you do it, you get a list of content where people recently have shown interest in. And yeah, one of the obvious disadvantages of that approach is that every user sees the same content, but on the other hand, it's fairly simple. Still, it needs optimization, because what's a good age of a post? So Yodel is, compared to other platforms, not only hyperlocal, but typically also hyper recent, because users are used to see very recent content and interact with their surrounding. So a 48 hours old post may be entirely irrelevant to them. So, and of course, we are not the first social media platform, neither are we the only one that actually cares about content recommendations. And so therefore you will see that things like HackerRank or Reddit also employ such formulas. And I just gave here one example from Reddit where you can actually see a formula. I mean, I will not go into full detail here, but in general, it's a simple approach that you have a very simple formula that determines some score, and essentially it's a logarithm of something related to the engagement a post gets, and by applying the logarithm, you in particular have value on the first engagement. And then you also have, again, something with the engagement divided by this term here, which essentially penalizes the time. And the idea is, the more recent a post is, the easier it is to get a higher ranking, essentially. And by doing so, you can still have a little bit older posts that really have a lot of engagement, and you can also and you also favor a more recent post, and also something specific, maybe in the case of Reddit, they also have a mechanism that they want to have less controversial posts, so for example. But this is already a certain thing that you need to optimize. And so we also played around a little bit with a hot sorting formula, and we came up with a somewhat different formula where we not only took votes, but we also have a concept that's pinning in our app. So you can pin a post, which is essentially bookmarking something. And this also expresses something like interest in a certain topic, but it's maybe not as vocal as an upvote or something like that. And on top of that, also on our platform, we have upvotes and downvotes like other platforms too, but they're not equal. So people tend to upvote a lot, but rarely downvote. And you should maybe also try to reflect this, because a downvote is sometimes already something like people, I wouldn't say they want to flag or block it, but it's maybe a step ahead of this. And this is why we created also a similar formula, something along the lines of what Reddit and Hacker News had, but then we also had to optimize it for different countries and different communities, because user behavior in different countries is very different. Sometimes they vote a lot more, sometimes they do less, and essentially we have to optimize it now for every community so that the formula actually works. And so we then tested a few rounds with the hot sorting, came up with a formula. I just want to show you some examples here. So this is now for one community, and there is a handful of posts. I mean, looking at the first post, maybe it's a little bit it's maybe fun or joke, somebody talking about first dates and stuff like that. You see, I think it's not that easy to see, but that post really got a lot of upvotes, has overall high score, let's say, and it's also recent. And then there's a second post or a second picture that was actually also made it into the ranking, which is very different, not only in the nature of the picture, but also when you look at the score, it's already quite a bit lower. The post is older, it's a totally different scenery, and apparently this got a lot of pins. And so by doing so, if you click through also the other of those top 5 examples, the next one is a text example, more recent, but got a lot fewer upvotes. And then again, another text post, which I'm not going to read out loud here now because it's German anyhow, and another picture. And then if you look at the content, then you will realize it quite large variety, and some of them just receive a lot of upvotes, and then you will also see that images in general tend to get a bit more upvotes, for example, and then by looking at it you might introduce a bias and something like that. And I mean, in general it generates interesting content, but it may not be, let's say, the last thing you want to try in on your mission on content recommendations. And in summary, I think clearly advantages are, it's a fairly simple formula. You can easily optimize it yourself for your particular use case. It is very easy to calculate, doesn't contain a lot of resources. And but there are also the disadvantages that I already mentioned earlier, that it's non-personalized and you still need to optimize something. And now the optimization is always the challenge, because optimization in this case means for us an A/B test, because you really need to test it in the wild, and then you need to wonder how you're going to present it to the user, so it's not that straightforward anymore. And nevertheless, I mean, while we're still also using hot sorting, we also then started to look into something, let's say, more in the area of machine learning, or we said, okay, let's try to make this personalized, and let's also make more use of all the data that we got. And this is why we started with collaborative filtering. I can imagine that many of you know what collaborative filtering is. Probably 20 years ago, something like that. This field was also largely pioneered by companies like Amazon. Something also very famous was the Netflix challenge, where Netflix actually had a challenge where the first company that would beat their internal algorithm by a certain amount in a certain measure would be granted, I think, $1 million. I'm not sure anymore, but this challenge as such already really pushed the field of collaborative filtering, and there's still some of the winning approaches that were used back then are still, let's say, today comparable to neural networks. And what's the idea of collaborative filtering? For those of you who haven't heard about it, it's essentially that if a user A has the same opinion as a user B on a post, A is more likely to have B's opinion on a different post than a randomly chosen post from all of the available ones, and by a random person. And this also then allows to recommend posts based on personal preferences. And what's still challenging is what's same opinion here? What does it mean that user A and user B have the same opinion? And how do you encode that understanding with the available data that you have? And here in this talk, I will more focus on matrix factorization. So when you talk about collaborative filtering, there are also various other approaches, so neighborhood-based approaches, so on and so forth. But I will talk about matrix factorization because what I really like about it is that it's also very easy to visualize. Now, the question, why are we using collaborative filtering, for example? So in first place, we didn't want to use a content-based approach because Yodel is active in various different regions. So we are big in the German-speaking countries, but we're also big in the Nordics, and we are big in Middle East and North Africa. Now, if you take a content-based approach, you would need to apply natural language processing in various different languages. And since our data science team is 5 people at the moment, it's essentially not doable. Although we have a community team where people would speak, for example, Finnish or Arabic or something like that, still collaborative filtering works on the more shallow level, and you don't need language understanding. Then also, we don't only have text, we also have polls, videos, images, and in the best case, we would like to recommend all of that kinds of content also. This is also another advantage of collaborative filtering, because it solely works on engagement on posts, for example. And then lastly, it is more complex to implement than hot sorting, but what you will also hopefully see during the talk today, there are sufficiently many collaborative filtering libraries readily available that you can easily deploy. So what's the input data actually for collaborative filtering? So there are different ways how you can do that. You can use explicit filtering, you can take explicit feedback, things like you would see on an Amazon page or Netflix, where you explicitly ask, hey, rate this item from 1 to 5. But it's sort of difficult because it is not really a part of our user experience and people wouldn't rate content. Then you have implicit feedback, something like an upvote, a downvote, or something like that. That can be also like measured as a feedback, and you can also then consider things like a share, because if I share something with somebody I know, it may be even stronger implicit feedback. It doesn't give it really, let's say, a number, but it's definitely something I might like a lot. And then there's also the most simple form, which is binary feedback, which is if you just take upvotes, for example, and take everything else as essentially unknown. And today I'm just going to talk about binary feedback because it just makes the setting a lot easier. Because if you go to, let's say, implicit feedback, you would have to talk about again, okay, is now a share 5 times as much worth it as an upvote? I don't know, probably community specific, user specific, who knows? Now, how does matrix factorization work? The input is actually fairly simple because we here also, as I said, are only taking upvotes into consideration, and then you would simply build a matrix, which is n times m. So n is the number of users in your community, for example, and m is the number of posts in a specific time frame. Let's take, for simplicity, think also what I'm going to use later in the examples is, let's say, 4 weeks of data. And then you essentially set every cell of that matrix to a 1 when a specific user upvoted a particular piece of content. And then you just get a binary matrix. And if you consider, let's say, our communities, they have tens of thousands, hundreds of thousands users, same amount of posts, then this matrix can also get, let's say, quite large, and then you probably typically would work with sparse matrices, but it's still fairly simple input, I would say. And then here's a tiny example just to highlight again. So let's assume we would have in total 4 different users, and we would have 6 different pieces of content. And a line indicates essentially that a user upvoted a particular piece of content. And now in this setting, it's we are wondering for user 1, we are wondering what to recommend to that user. And as you can see, it's a fairly small example, and you can already see here in the matrix that there are, let's say, maybe certain blocks or something like that. Obviously, I mean, it is a toy example, but this would be the simple input. Now, what we could do is, let's say we stick to adapted hot sorting. Now, all of this doesn't contain the time dimension because I wanted to keep it simple, but what would adapted hot sorting or any engagement based approach do? It would just look, okay, what has been upvoted the most in the past, and I would recommend that piece of content to the user. Now, in this particular case, we can see actually here that this piece of content number 4 has been upvoted in total 3 times. And so we would recommend that piece of content to that user. But maybe this user doesn't share any similarities with 3, 4, and 5, because as we said previously, we would like to recommend something to that user if we find similar users that have shown similar engagement in the past. So this is the reason why, yeah, adapted hot sorting may not be the best choice here in this example. Now, as opposed to that, if we go back to the idea of collaborative filtering again, we see that user 1 had the same opinion on post number 1, which is essentially here the first column. Unfortunately, you can't really see my pointer, but at this small example, you would say that user U1 is more closely related to U2 than the other users. So looking from that perspective, we should also rather recommend content to that user that has been liked by U2 in the past. And this is pretty much what matrix factorization will do. Now, how does it achieve it? So this is pretty much the only formula in my talk. I mean, it's almost probably 8 o'clock by now anyhow. So let's make that fairly simple. It's a very simple dimensionality reduction, essentially. What you try to do is you try to split your original input matrix into 2 other matrices with a smaller dimension. And you try to do it in such a way that if you multiply those 2 matrices with the smaller dimensions with each other again, and then the distance to the original matrix should be as small as possible. And of course, if we look at the formula, we would also say, okay, but now for W and H, which are those 2 submatrices essentially, we need to define a dimension. And we can also have, on top of that, when we do that, we also have when we multiply those 2 matrices again, we have the nice advantage that wherever there is a difference between the 2 matrices, essentially, it indicates to us something that content can be recommended because it diverges from the original input and essentially says the multiplication expected a different value, essentially. And I will go a little bit more into detail now in the next slides. And when we look at W and H and we think about it as a matrix or as a dimensionality reduction approach, we also have to think about, okay, what are the, yes please, the dimensions?
Yes, so matrix matrix V is dynamic, right? I mean, so first matrix, the original matrix, which you decompose,
yeah,
is dynamic because I mean, post 1 is going to leave after some time, and extra colors are added at the back, right? So it's basically a shifting matrix.
Well, it's definitely dynamic. How it is shifting, it's always a question. It's definitely also like that for example, the newest content can only get, let's say, engagement in a certain time window. So for example, why time splitting wouldn't make sense if in the evaluation. But also when you look at matrix factorization, essentially, you don't train a model in advance like you would do it for other supervised methods, but instead you do it on the fly, essentially. So we regularly train and then do a prediction at the same time. So essentially, every other hour, or depending on the velocity of your feed, you would do it again because you essentially have new engagement. And also with every recommendation we do, we would have impact, hopefully, on that input matrix. Yeah, exactly. And then what I just quickly want to say, if we do the dimensionality reduction or matrix factorization, we have to think about a dimension for W and H so that we can multiply them with each other again. And this is essentially the number of latent factors or dimensions. Here in this toy example, I will just use 2 because then it's still fairly simple to visualize. Of course, in the real world, this is also yet another thing you have to optimize for. And essentially every factor is something like, you can think of it as a cluster of content, where you on the one hand cluster topics, cluster posts, because you will have posts together in one cluster that are liked by a similar set of users, and also the other way around. You will have clusters for users that are similar in terms of their engagement for specific posts. Now, yeah, okay, and yeah, I think it's still large enough, right? Yeah. I mean, I have no clue what I pressed, but yeah, I mean, anyhow. Reminding us of the idea again, so what was the matrix factorization again? We take this input matrix V and we want to decompose it into two matrices that have here in this example, each of them have dimension 2. And if we multiply those two matrices with each other again, we want to be as close as possible to the original matrix. Now, if we run that optimization, we would get something like that, what you can see here. And as you can see here already, you see in W already certain clusters, because you see a lot of zeros, which essentially says those users don't belong to that cluster. And you see the other positive values, which indicate that, for example, the users 1 and 2 rather belong to the cluster or factor 2, while the other 3 users rather belong to that other cluster. Of course, a toy example, this was exactly what I wanted to show, but also, let's say in a real world example, you would see certain clusters, how users group. And you can also see the same with the posts, that you can see, yeah, we have 2 topics, so to speak, and rather the posts 4, 5, and 6 belong to that first one, and the other one belong to that other cluster. Now, if we look at the example again, what I tried to say earlier now, if we multiply those two matrices with each other again, we want to be as close as possible to the original input, and whenever we diverge, we take this as an indicator that it should be something we recommended, because the optimization would suggest that it should not be 0 as an example. And now if we exactly do this, this might be a little bit small now, but as you can see here, the resulting matrix has exactly the shape what I mentioned earlier that you see here. Maybe I'll just walk over. Here in those cells which were initially 0, you now have positive values, and essentially all the other things, the 0 blocks, are still kept, and you can see that we can now actually use this information to recommend something. And this is exactly what we're seeing here. If we're now multiplying the first row with the second column, for example, because we want to have a value for the likelihood that user 1 enjoys post 2, we will see it's a non-zero value, and it is let's say together with the third post the highest values, and we would predict we would use this as a prediction and make the recommendation to that user.
Yeah. So the bottom row in the H matrix says F1 2 times.
Right, that should be F2. Yeah, sorry about that, but it's essentially the factor from the and what you can also see here in this example now, again, what I mentioned earlier, that you find those nice clusters that essentially user 1 and user 2 really enjoy more the post P1, P2, P3, and there's the second cluster of users that really enjoy the other topic more. And if you wanted to implement this now, maybe let's say on any small use case where you want to do recommendations, it's essentially everything that I showed are those 10 lines of Python code. I mean, this example here, it's simply I'm using sklearn for the Python library. I am using SciPy here for sparse matrices, and you would simply just use the NMF implementation from sklearn, and then you could simply do it really in those lines of code, and the resulting matrix would be exactly what I just showed to you. And of course, I mean, if you now do this, if you run it on a real-time, in a real-world data set, you will encounter a few more challenges, but nevertheless, I want to show you a few examples. So we did pretty much that, ran it on a few communities in Germany. I think in total, the images that are the examples that I'm showing here, we ran it on a data set with around 10,000 users, roughly 44,000 different posts. I think it contained roughly 300,000 interactions. Now, if you think about 300,000 interactions, but a matrix that is 9,000 times 44,000, then you will see this is extremely sparse. So even if you look at literature, you will see that typically it's maybe 1% or something like that in terms of the density of those matrices. And in this particular case, it's even less than 0.1%. So this is definitely a challenge, and you will also see in the literature, in particular, certain algorithms and approaches do better or worse with this extreme sparsity of our input matrix. But nevertheless, we took that algorithm here, ran it on some data, and now what you can see, and this is also again with respect to the clusters, if you run the matrix factorization and you just take a look at your matrix H, then you will see essentially for every factor, you will see which posts match this factor most. And when you plot that, when you plot the top 50 posts for each factor, for example, then you see something like that. For example, the top blue line is something where we would say, okay, the first post in that bucket has the highest value of 3 point something or something like that. And you see those curves essentially. And you see if they have, let's say, an extreme, linear relationship, or let's say not such spikes, it's more coherent maybe, and those are cases where you really have, let's say, almost two outliers, but which are still very much speaking for that cluster. And when you now think about, okay, what's shown on Yodel, we're not that similar to Nextdoor apparently, because what you will see on Yodel, cats. So easily detectable is a cluster like that, where you essentially have the top 5 posts in one cluster are cat images. I must admit that I actually chose that image because it works so well language agnostic. And also the second cluster that I just want to show is also maybe, let's say, pet related, because it's just so so easy to show, because all the other clusters that contain text and I have to translate, or it's difficult to translate maybe sometimes the gist of it. But as you can see also here, while the other one was, let's say, fairly straightforward, we have channels, for example, Yodel Zoo, and I would bet that probably those 5 posts came from that channel. But also here, it's already a little bit different. I mean, and you can see, but it's still, they have a certain topic, I would say. And this is really what you already get from non-negative matrix factorization and very simple interactions. And now when we actually optimize our models, it's always a question, okay, what should we go for? What metric should we actually optimize? You will see a lot of literature that actually uses initially rooted mean square error, because you have those 2 matrices, and you can say, okay, if the error is low, then we're doing better. But it's also not super easy to interpret, but because what does it mean to have a certain RMSE or something like that? This is why we also work a lot with the average reciprocal hit rate, which is actually going more into that direction, that you want to find hits essentially. You want to make in a holdout set, you want to make recommendations that the user actually interacted with, which is much closer to the user experience that we want to positively influence. And this is also then again what we talked earlier a little bit with the testing. It's not that easy, because when you do essentially holdout set, you can't really do it time-wise. So you cannot just say, okay, what would the user have voted on in the future, because you may remove all the newest posts from your data set, and then essentially you don't have them in your matrix and you cannot make a prediction for them. And what I would say is, let's say in our setting, maybe uncommon is that we have a comparably long list of recommendations, because when you remember the first images, we have this huge feed, right? I mean, this is a feed of endless content, and we want to, let's say, mix in recommended content, so we cannot just have 3 recommendations or something like that. And many of the evaluations on recommender systems you will see are maybe just taking 3 recommendations into account, because if I want to recommend a movie or something like that, people will not scroll through 75 movies maybe, but the first 3 need to be something that they're really interested in. And then there are also other things that we are also taking into account, which is something which I don't have more details here, which is the personalization score, because eventually what we also really want to do eventually is really diverge from hot sorting in that sense, that we really make personalized recommendations. And now I think no, I think it's just because I'm not in the presenter mode anymore, and this is why I think yeah, I mean, probably let's hope that it's not 2 minutes again. But I think anyhow, I mean, just to wrap up, only 1 or 2 slides left anyhow. now you will probably wonder, okay, is this all that we do, and is this really the best way of doing the best possible recommendations? Probably not. But what is really nice about matrix factorization or non-negative matrix factorization, in its example, that is really intuitive. You can implement it easily, but there are several other methods also in the area of matrix factorization which have been suggested, proposed, let's say also in the last 5 to 10 years, also in combination with Netflix, for the Netflix challenge, for example. And there are also other ways of doing a matrix factorization. So NMF works with a coordinate descent, but there are also approaches like alternating least squares. And for example, in our use cases, we have already seen if we replace the non-negative matrix factorization by alternating least squares, we can easily outperform NMF in terms of the average reciprocal hit rate, for example, that we have seen scores 7 to 19% better, but it would also take roughly 25 to 50% longer. And now if you think about it, we run our data science stuff in the cloud and they bill us by the minute. So those 7 to 19% improvement also really need to map to a business value, because that's not clear at all. Does that mean that I only have one user who clicks one post more? I don't know. And this is, to be fair here, this is also something that we're still investigating. How is this mapping actually working? And also when you go beyond, let's say, matrix factorization or something like that, there are also still plenty of, let's say, simple linear models. For example, SLIM, it's actually called simple linear method or model, which is even better in our cases than ALS, and still it's a linear model. So it's still straightforward to calculate. And even here, when we talk about, when we talk about runtimes, we are not talking about hours, right? So what I will also say in one of the last slides when it comes to pitfalls is actually the fact that for us, the data engineering side is still one of the bigger challenges, because we have so much data that it's actually generating the matrix can be more time consuming and more costly than actually running the algorithm. So as an example, when even if it's 50% more, but if it's only seconds, minutes, or whatever, if it takes half an hour to get the data, that's one of the challenges. And this is also what I want to say here on my last slide here. Actually, pretty much what's not shown in the code is actually all the other challenges that we face. So if you collect hundreds of millions of events every day and now want to do a recommendation for one particular community, the data engineering effort and getting this data, this is already a comparably big time-consuming task for us at the moment, for example. And in particular, if you say, okay, I want to regularly have data from the last 28 days for this particular community and something like that, then also what I touched upon already is the business value. So what does it actually mean? Is it worth it to have a 7% higher metric, whatever, and does it justify more costs? This is something we still need to look into better. Then also, unfortunately, it's also not that easy to test all of that, because now if you have two competing models, you need to run an A/B test, and we are a community. So you're essentially affecting one part of the community, but not the other. But then they will know that they're in somewhat of an experiment, because they will complain about something, and then other people just say, no, I don't see recommendations or something like that. So setting up a proper clean A/B test in this setting is not easy. Then on top of that, if you look at user behavior on social media platforms, it's not uniform. It's not that every user adds their certain amount of engagement to the overall engagement. Instead, you often have those Pareto distributions where, let's say, 20% of the users are maybe responsible for 80% of the interactions. And now you want to make an A/B test and you want to show that your method is maybe 5% better. But much of it may just be influenced that you didn't do a very clean random split with your users, and you have two more power users in that one group, and then try to make a significance test here. And then also there are other, let's say, just the technical challenges, all the parameters. I mean, there are dozens of parameters. We need to find the best metric for us that when we optimize, that we then really optimize for user value. So that was pretty much it of my talk. Last but not least, here is now the advertisement block. I'm sorry for that. In first place, I want to invite all of you to join our Cologne AI and Machine Learning meetup group. And this is probably also the last chance for you guys here to join a meetup virtually. And there's actually another funny coincidence, because not only is our next meetup about recommendation systems, so if you're genuinely interested in recommender systems, you should join, but also that our next speaker is actually a former colleague of Martin. So we have Barry Karasberger from Bowl.com, who will talk about retail recommender systems. And yeah, funny coincidence. And as far as I know, he also used to be here in Utrecht. So join our community and maybe join us, maybe even in person at some point when you're in Cologne. And if you do so, I can guarantee you that there will also be a nice Kölsch for you waiting. And so the last advertisement, of course, is that we at Yodel, we are a growing startup, and we always have open positions, in particular in engineering. And this is not only data or data science. At the moment, we are looking for back-end engineers. So if you're interested in also other sides of hyperlocal communities, or generally in that space, I can only invite you to take a look at our jobs page. And also we have currently open positions in SRE. So I can definitely tell you that the challenge of just maintaining and running a infrastructure like ours, it's super fascinating and it's really interesting. And so that's it with the ad block. And now maybe a few minutes questions. Thank you very much for your attention.
I think we have some questions already.
Yeah.
Yeah.
Have you considered like explicitly turning those communities into like a graph? Like if you turn it into a graph, you can actually apply things like, for example, you can use degree centrality, find similar communities, and then you don't have to recalculate only based on content, because you know based on the content that certain people are part of a certain community. And then based on the connectedness of those communities, you can recommend posts without having to recalculate the.
Yeah, we actually we have done something like that. It actually precedes the time when I was there, and we did something similar, like a graph-based approach, where we said, okay, we also try to find, for example, author information and connect users if they like content of the same author and something like that. Back then, the challenge for us was to actually run that code, or let's say deploy that code in such a way that it's fast enough. That was one of the challenges, because if you then deploy a graph-based approach, you always have to calculate the graph and something like that. And one of the advantages of collaborative filtering or matrix factorization is that you can really easily cache that information, and that you then have that readily available. But it's still something on our minds, and we still also want to combine those things, because you could now also think about, how can I encode this, maybe this kind of information, maybe in my input matrix V, for example, or something like that, that you have, let's say, maybe columns for specific authors or something like that. But graph-based is also super interesting, and it's also something maybe to other people, non-technical people, even easier to understand, because we always try to be in touch with product. So what is actually the user behavior and something.
Yeah. It's also really interesting from like a bot detection perspective, because there's quite a few algorithms for.
Yes, definitely.
Once you have one bot, you can detect people or like links with similar.
Exactly. Yeah. I mean, definitely. Also, I mean, I think my perspective on bot detection right now is actually that I think the maybe most low-hanging fruits are actually more on, let's say, early behavior, because they often do something like they do a location switch in seconds, and what you can't do as a human, or you upvote 10 posts within 2 seconds. But besides that, I agree, because you also have people that behave perfectly fine for a certain period of time and then start maybe also unwanted behavior or something like that, or are not, or are more clever and don't have malicious behavior at the first day. So more questions? Yes, please.
You mentioned that you periodically have to retrain this matrix, recalculate the matrix. How do you do that? Because I can imagine it's too much work to do it by hand.
I mean, in all honesty, the most time-consuming part right now is the access to the data essentially. So getting all the interactions a certain group of users have done in a certain location. So if once you have that data, building the matrix from it, it's super fast, and even the matrix factorization is comparably fast, or if you use even Slim or something like that. But it's one of the, let's say, engineering challenges that we currently face is really make, let's say, 4 weeks of data of a certain community readily available so that you can have that within, let's say, minutes, that you can do recommendations every hour. And we also want to have low latency, because if you just liked something, this is maybe even your strongest interest at the moment, because there's also, let's say, certain decay in time. Things that you have liked weeks ago maybe are not as interesting to you. And this is also, data engineering at Yodel, also something where we are definitely looking for people who are interested in that.
If you can't find them, we'll help you out remotely. So
that's definitely good. We are always also open for exchanges on those topics, because I think that's really also, I think, the foundation of all that we do. Yeah.
Any more questions?
Can I just have something clear? Because the amount of clusters is an outcome of the decomposition, right?
And the number of clusters you choose in advance.
Ah, right.
So these are the dimensions that you have to feed into your optimization.
Yes. So you're basically right. Okay. So you're not clustering on the weight matrix itself.
Well, you are in a certain way you're clustering the input matrix V. And you essentially say in advance also the number of clusters that you,
All right. Fabian, Olaf, I got you something. Hope you can see it. You have Kölsch in Köln.
Yes.
We have the Lekkere in Utrecht. It's a local beer. Everything is lekker in Holland. That's what I learned when I got here. So I hope you also find this beer really lekker. And thanks a lot for coming. Olaf will send you this to your vacation thing, so you'll receive it shortly. Thanks a lot for coming.
Thank you very much for the invitation. Really enjoyed it, and I will definitely compare it against Lekker Kölsch, and then
Indeed, we'll drink one together.
Thank you very much. Yes, let's.
All right, everybody. Thanks a lot for joining this first.